In this lesson, we're going to be looking at an alternative formulation to Lagrangian mechanics, and that is Hamiltonian mechanics. And you may remember that we saw something called the Hamiltonian in the lesson on Noether's theorem. In fact, the Hamiltonian we're going to see today is the same Hamiltonian we saw in Noether's theorem, except now, more than just being the energy or the conserved quantity associated with time, we'll see that we can get equations of motion from the Hamiltonian. The key difference between Lagrangian and Hamiltonian mechanics is that the Lagrangian uses second-order differential equations. So for each generalized coordinate, there is a single second-order differential equation coming from the Euler-Lagrange equation. For the Hamiltonian, for each generalized coordinate, there are two first-order differential equations, and these are Hamilton's equations, and we'll see them at the end of the video. To go from the Lagrangian to the Hamiltonian, we need a mathematical technique or a mathematical tool called the Legendre transform. And that's what we'll see during the start of this lesson. And finally, you need the Hamiltonian if you want to do quantum mechanics or statistical physics. You might be content for the Lagrangian for classical mechanics, but as soon as you want to do quantum mechanics or statistical physics, or some other areas of physics too, you need the Hamiltonian. So we're now going to go through what the Legendre transformation is. So assume we start off with a function, just f of t, just an arbitrary function. And we also have its derivative, df by dt, which we're going to call s. Now we can invert these and make everything a function of s. So we have t of s, and we have f of t of s. So once we substitute in for t of s, f is now a function in terms of s. And note there are some technical assumptions needed to do this inversion, and these are discussed in the booklet, but we won't go through them here. And then once we've inverted the function, we have our Legendre transform, which will be a new function, g of s, and this is just equal to s times t minus f. And we've substituted in everywhere, every t in terms of t of s. So if we write this whole thing out, it will just be in terms of s's. There'll be no t's anywhere. And if we take the derivative of g, so we do dg by ds, this is equal to t. So kind of what we've done is we've swapped f with g, and in doing so, we've swapped t and s around. So originally we had f of t, we now have g of s, and where s was our derivative before, t is now our derivative. And the coordinate, or the quantities s and t, are known as conjugate. We're now going to see an alternative way to think about the Legendre transform, but the end result is exactly the same. So once again, we start with our function f of t, and the derivative s equals df by dt. And then we look at the differential. So df equals df by dt, dt. And we know that df by dt is s. So our differential is equal to s dt, where s is defined to be df by dt. And s and t here are called conjugate, as before. And then our transformation, as before, is g equals st minus f. And so if we take the differential of g, we find it's equal to t ds. So again, once we've taken the derivative, we've swapped s and t around. So once again, the Legendre transform swaps f and g, and it swaps s dt for t ds. We're now going to go through and calculate some conjugate variables, and then do some Legendre transforms. So for part A, we want to find the conjugate variables to p and q. So the conjugate variable to p is m, which is df by dp, which just gets us 2p plus 2. Now have a go and work out n on your own and come back to the video. Okay, to work out n, we do df by dq, which is equal to minus 2q. And then to make things easier for later, we're going to invert these. We want to find P of M and Q of N. And so we have P equals m over 2 minus 1, and Q equals minus n over 2. Then for part B, we want to calculate the Legendre transform between Q and n. So we start off with our function g, which is Qn minus the original function f. Then we substitute in for f. And then this is a function of p and n, not a function of q. So we substitute in for q in terms of n. And then we can simplify. All right, have a go at C on your own and then come back to the video. Okay, to start with, we have the definition of a Legendre transform with two variables. So we have Qn plus Pm minus f of p and q. It's just like we did before, but with both pairs of conjugate variables. Then we substitute in for f. And then this is a function of m and n, not a function of p and q. And so we want to substitute in for q and p. And then we get our final result. Right, this example is a bit different, but if you've done a course in thermodynamics, this should be very familiar to you. So we have a function u, which is a function of s and v, and we've got its differential there. So in this example, t and s are conjugate variables, and p and v are conjugate variables. So firstly, we want to define t and p in terms of partial derivatives. So we expand our differential, so du equals du by ds, ds plus du by dv, dv. And then we can compare it to above and we get t equals du by ds, and by matching up the dv's, we have p equals du by dv. Now for part B, we want to see what Legendre transform is needed to give a function that is a function of t and v, not a function of s and v. So remember that when we do the Legendre transform, we swap conjugate variables. So we want to do a Legendre transform between s and t. So f is equal to ts minus u. Now for part C, have a go. What Legendre transform do we need to do to work out the function h, which is a function of s and p instead of s and v? Okay, the Legendre transform we need to do here is a Legendre transform between p and v. So h is equal to pv minus u. And with both of these examples, and I would recommend doing it, take the differential, so work out df and dh, and expand it like we did in that first line above. And you'll see we get something similar to the first line, except the ds and dv get replaced by whatever arguments are in the brackets of f and h in the question. We're now going to look at how to define the Hamiltonian, or how to get the Hamiltonian from the Lagrangian. Remember we said that this was going to be a Legendre transform. So we start with our Lagrangian, and what we're going to do is do a Legendre transform with the velocities. So we're going to get rid of the q dots. So the Hamiltonian will just be a function of q, the conjugate variable to q dot, which will be p, and t. So we also need to have the conjugate momentum, which is dl by dq dot. So the conjugate variable is called the conjugate momentum. And then to get the Hamiltonian, we Legendre transform between q dot and p, where the sum over I is just to remind us that it's over all generalized velocities. And this is the same conjugate momentum we saw with cyclic coordinates. So just as the Hamiltonian we saw when we were talking about Noether's theorem, again we saw the conjugate momentum when we were also talking about symmetries. We are now going to look at some examples where we calculate some Hamiltonians explicitly. You should remember this Lagrangian as a pendulums from previous lessons. So to calculate the Hamiltonian, we firstly need the conjugate momentum to the velocity. So the conjugate momentum to theta dot, and this is given by ml squared theta dot. Then the Hamiltonian is the Legendre transform, and then we substitute in for the Lagrangian, and finally we want the Hamiltonian to be a function of p and theta, not a function of theta dot. So we rearrange our top line for theta dot and substitute that in and simplify. This is our second example, which you may remember as a ring that was forced to spin and a particle can slide around the ring. So have a go at this on your own and then come back to the video. Okay, so now you've found the Hamiltonian, I'll put the solutions up. So the conjugate momentum is just like before, ml squared theta dot. The Hamiltonian is the Legendre transform. We substitute in for L. Then we need to get rid of theta dot, make sure everything is just a function of p and theta. So we solve for theta dot and substitute this in. And here, we may think the Hamiltonian is energy, so it would be kinetic plus potential, and it was in the previous example. But here, there's that second term in the kinetic energy of the Lagrangian, which comes from the fact that the system is driven externally. And because of that, the Hamiltonian is no longer just potential plus kinetic. We are now going to find the equations of motion in terms of the Hamiltonian, and this is sometimes called Hamilton's equations. But before we do that, we're going to need to find a quick result first. So we already know that the conjugate momentum is the derivative of the Lagrangian with respect to the generalized velocity. And now what we want to show is that the time derivative of the conjugate momentum is equal to the derivative of the Lagrangian with respect to the generalized coordinate. And we're going to need these to derive the equations of motion later. So to show this, we start with the Euler-Lagrange equation. And then we substitute in dl by dq dot for the momentum. And then this first term is just p dot, and therefore p dot equals dl by dq. We are now going to derive the equations of motion. So we start off with the Hamiltonian in differential form. So we've taken the differential of the Hamiltonian and rewritten it in terms of partial derivatives. We can also take the differential of the Hamiltonian in terms of the Legendre transform, like we did at the start of the lesson for other Legendre transforms. We can now expand this using the product rule. We have q dot dp plus p dq dot, take away the differential of the Lagrangian. Now we can substitute in dl by dq for p dot and dl by dq dot for p. And then those two terms cancel, the two dq dot terms. And this is what we'd expect from a Legendre transform. All the terms left are dp, dq, and dt, which are the variables the Hamiltonian is a function of. It wasn't a function of q dot, and so the dq dot terms have cancelled. We now simplify this, and then we can work out the equations of motion by matching up terms on the very top line and that bottom line. So firstly we can match up the dp term, and we see that q dot is dh by dp. Then we can match up the dq term, and we see that p dot is minus dh by dq. And then finally we match up the dt terms, and we see that dh by dt is minus dl by dt. And remember, most examples we've seen or you're going to come across, dl by dt is 0, and the Hamiltonian also won't depend on time. So that last equation of motion is often irrelevant. Nothing depends explicitly on time. We're now going to have a couple of examples where we find the equations of motion explicitly using Hamilton's equations. So to find the equation of motion for this Hamiltonian, we start off with p dot equals minus dh by d theta, where theta here is our only generalized coordinate. And then we do the derivative and we have minus mgl sine theta. And then the Hamilton's equation for theta dot, so theta dot equals dh by dp. Again, we do the derivative and we have p over ml squared. Okay, have a go at this one on your own and then come back to the video and I'll put up the solutions. Okay, now you've had a go, I'll put the solutions up. So here's the solution for p dot and here's the solution for theta dot. We're now going to look at energy conservation, and you may remember that the Hamiltonian is the conserved quantity associated with time translation symmetry. And so to see if the Hamiltonian is conserved, we want to see if the full derivative with respect to time is 0. We've already seen the conditions for the partial derivative with respect to time to be 0, and that was just that the Lagrangian had no explicit time dependence. But what is the condition for the Hamiltonian to be conserved along the trajectories particles take? So now this is the full derivative, not the partial derivative. So to start off, we expand this using the chain rule. And if there were multiple generalized coordinates and generalized momentums, we would sum over all of them. But I'm just going to assume there's one generalized coordinate and one momentum. So now we substitute in for Hamilton's equations for dh by dp and dh by dq to get q dot and p dot respectively. And now we see that those first two terms cancel and we're just left with minus dl by dt. So in fact, the condition for the Hamiltonian to be conserved is exactly the same as for the partial derivative of the Hamiltonian with respect to time to be 0, which is quite a remarkable result. So in summary, the conjugate momentum is defined as dl by dq dot. The Hamiltonian is given by the Legendre transform between q dot and p. And when we work this out, we have to substitute in for q dot, so that the final function is just a function of p and q, and not a function of q dot. And then finally, we have the equations of motion in terms of the Hamiltonian, otherwise known as Hamilton's equations, and they are q dot equals dh by dp, p dot equals minus dh by dq, and then the rate of change of the Hamiltonian along a trajectory, so the total derivative of the Hamiltonian, equals minus dl by dt.